Okay, and now we will move on to the last talk of this session, and that will be from Dr. Phil Erickson, W1PJE of the MIT Haystack Observatory, and he's going to be talking to us about amateur digital mode based on remote sensing, FT8 use as a radar signal of opportunity for ionospheric characterization. Okay, Phil, go ahead.
Thank you very much. Let me see if I can share my screen correctly here. All right. Can you guys see my screen?
Yes, we can.
Okay, great. So it's very nice to virtually be here, and I probably get minus points for having too long of a title. This is a work that has essentially been in progress for a little while now. And I want to point out my co-authors, who are Bill Lyles, NQ6Z, and Ethan Miller, K8GU. It's been a real collaborative effort, so I'm really honestly just reporting most of the hard work that the other folks have done. I'll go over why an overview of FT8 itself and why we might be looking at it in terms of an ionospheric remote sensor. I will talk about these things called radar ambiguity functions, which may be familiar to some if you've ever taken a course on radar or had some design experience with radar, but may not be familiar to everyone. And then what we're going to try to do here is see, hey, there's a lot of FT8 signals out there. Can we use some of them as a forward scatter remote sensor of ionospheric properties? I want to emphasize this is the beginning of our study, and there's lots more to do, but I'll give you sort of the highlights of where we ended up initially. So these are digital modes from our friends Joe Taylor, K1JT, and Steve Frank, K9AN, which have certainly swept the amateur community in the last 3 or 4 years as being really transformative, especially when we're talking about weak signal propagation or very low signal detection in the current solar minimum conditions that we're living in. These have really been a game changer for small stations to be able to make contacts. The interesting thing, by the way, there is a bit of a connection here in that Steve Frank was actually on Ethan Miller's PhD committee, so he even has a direct connection to this, professor at the University of Illinois. These were designed by Joe and Steve and company to be weak signal codes, and they're one of a suite of codes that sort of labeled WSJT, weak signal Joe Taylor. And they are things that are designed to be used in SSB audio bandwidths, which a conventional transceiver can be used. And they basically use some of the best coding theory that are out there for doing really robust error correction built-in communications. And the key design parameter in these kinds of things is EB over N0, which is the energy in a bit of communication divided by the noise floor in that bandwidth that you're transmitting the bit. And these are down to a few decibels above the noise floor. So they are really pretty close to state-of-the-art in these sorts of things, especially at HF. If you look down here on the left-hand side on the bottom, you'll see a typical WSJTX set of people transmitting and people receiving. And then figure 1 shows you sort of a block diagram of how you would send your message. There's an encoder. You transmit it through the radio, someone on the other end receives it, and they demodulate it. They typically use a combination of, some of them use low-density parity codes, and that's what we're going to be concentrating on today. Some of them use Reed-Solomon codes, and some of them use convolutional codes. And they have a very, very sophisticated deep decoder that uses a lot of interesting math to really pull out the last morsel of signal from a signal in the form of noise. So if you'd like to read, Joe and Steve have put up a nice set of really meaty papers on the soft decision coder, which is really interesting. Just for reference, the best human CW operator has been quoted to can tick out a signal in about a 50 hertz bandwidth if it's really, really weak. FT8 is essentially only using as much bandwidth as that best set of ears, but has a much better detection floor than conventional CW. This table on the bottom shows you the various kinds of codes. We're going to be focusing on FT8 here, which is a LDPC, which is low density parity code. I'll explain more about what those numbers mean in a minute. And, but it's obviously part of a suite of codes. So the question that our little group had was, can we use these things as a remote sensing ionospheric radar, really? And I like this table from one of Joe's articles because it shows you the various waterfall graphs of the various coding that is available in this suite. If we just focus on two things, we have the carrier over here. This is just basically a tone. You hold the key down, you don't do any modulation of it. And a carrier is a great thing for velocity. We just heard Steve Serwin talk about very accurate Doppler measurements or velocity measurements. That's really great. It has almost no range information in it at all. In fact, a CW tone has none. That's like a police radar, okay? It concentrates on frequency measurement at the expense of range measurement. If we look at FT8 over here, you'll notice that it's considerably spread in bandwidth compared to the carrier example. And so there's some range and velocity information that you might be able to pull out of that, because any signal that is spread some in bandwidth, there's something called the Rayleigh criterion that translates bandwidth into range information if you can process it quickly. So we thought, oh, well, there are some potentials for radar, okay, in here. And this is actually a slide that Christina made up that I've been using for a little bit. What do you do with measuring frequency, and what do you do with measuring range in our case? If you remote sensing the frequency shift, you're going to be measuring the Doppler shift, which is essentially can be related to the ionospheric velocity. We've heard from Steve Serwin. We're going to hear from other people later in this conference about, again, measuring and interpreting Doppler. I will point out that I also gave a talk at the TAPR DCC meeting in 2019, which is available online, called Challenges in Understanding WWV Doppler, just to show you that, as in many things, it's a little complicated to analyze this thing, but you can make some interpretations about what the Doppler means on your path. So that's measuring frequency, which we're interested in. If you measure range, a very classic signal that measures range is an ionosonde. You send a pulse, a limited thing in time at a particular frequency. You time how long the return takes, and from that you can then extract ionospheric information. In this case, you can recover some information about the bottom side electron density profile in the ionosphere. So in one case, measuring range is interesting. In another case, measuring velocity is interesting. So how do you figure out whether a particular transmission, especially one you do not control, like FT8, is useful for radar? Well, in the radar literature, there's this thing called the radar ambiguity function, and you can look up a number of textbooks and other references that talk about this. The idea is to evaluate how good your pattern is in figuring out how far away an object is, that's range, and what its frequency is, for example, Doppler shift, when the target may not be stationary, like it's moving in Doppler, which means it has a Doppler shift, as well as it may have a range extent. This thing called the radar ambiguity function, this is one of the mathematical definitions of it, but look at the picture down here. You make these little plots which are two-dimensional, and the color indicates the amplitude of your ambiguity function. The range is on the x-axis, and the Doppler is on the y-axis. And this is an idea of how poorly you're doing in your range and Doppler. The thing in the middle is what you want to measure. You want to measure the object at the precise range it's at and at the precise Doppler shift it's actually at. No code is perfect. All these other colors you see here are side lobes. Those are unwanted responses, so that anything, for example, in this little diagram, that's at a little higher Doppler and a little bit closer to you in range has a little contribution that kind of gets mixed up with the thing that you want in range and Doppler. And so the mathematics of picking a radar transmission signal is to attempt to determine how can I make that code look more like a dot in the center, which is called a thumbtack function. Kind of looks like a thumbtack sticking up, or a delta function. And I'll just point out that, yes, this one happens to be not an ideal code. It was used as an example.
Phil, we are seeing your presenter's desktop.
Oh, no, really? Okay. Has that been going on the whole time? Probably. Well, how about this? I will pause for one moment, and I will just share my desktop. How about that? And now, can you see my desktop? Can you see there? Thank you very much. So I've been explaining here that we have a, we'd like a thumbtack function. Okay, that's what we'd really like to head for. There's a very nice analogy that I want to point out. It's kind of like a blurring kernel in image processing. The original picture at the top is the actual object that you'd like to take a picture of, but maybe you have a lens, for example, that's dirty or that isn't the best lens, and you can mathematically deal with that by applying what we call a blurring function, which takes the original and makes the thing at the bottom. It makes a blurry example of that. So we'd like the thing on the top, the thing we measure is on the bottom. You can think of this in a radar sense as that this in here is mixing up the two-dimensional X and Y in the image. Here you can think of X as being the range and Y being Doppler or frequency. We would like as little blurring as we can. So it turns out that there are many coding examples of how you get toward not too much blurring. One of the simplest one is a pseudo-random phase code. You basically make a random sequence. In this case, I've basically created a 1024 long random code, which is a phase code, so it just goes between +1 and -1. You either shift the sign or you don't. And as you make that thing longer, on the left-hand side is my Doppler and range, and I've zoomed in on the middle at the right-hand side to show you that there is, in fact, a very nice, pretty close to thumbtack in the middle, and all that other stuff is little bits of confusion because it's a fairly long random sequence. And this is easy to explain in an intuitive way because a random sequence only perfectly correlates with itself. So it tends not to mix up range and Doppler. As you make the code longer and more random, it gets better. So this is a place that we might want to head for. So now let's look at FT8. There's a bunch of facts about FT8 at the top there, but the important things are that it uses 8 frequency tones, so that's 8 frequency shift keying, spaced out by 6.25 hertz. So it occupies a total bandwidth of about 50 hertz. And if you dig into the details, okay, and there's plenty of details in the bottom, this is one of these low-density parity codes. It takes 87 information bits out and then makes 174 coded bits. And then you've got essentially 8 tones, so each time period you can put 3 bits of information in there. And then the final thing that happens is that Joe allows for the fact that the receiver may have an offset, the clock on the computer may be offset in time, and the receiver may have drifted a little in Doppler, so he puts these things called Costas arrays at the beginning, middle, and end of the sequence, and those are in orange right there. And they are designed to let him search for the time and frequency offset of his receiver with respect to the transmitter. And so he assembles that whole thing into a payload that you see represented by that numbers. So what we wanted to do was take the blue part, never mind the Costas part for the moment, we wanted to see how random does that blue part, which is the actual coded message, poured through this very sophisticated low-density parity code, which has lots of error checking in it, how random did that make the message? Remembering back here that we'd like to head for that. So Ethan made this particular plot. On the top is what we call a message stencil, which means everywhere there's a yellow block, we're using that frequency, and time is on the x-axis. So for example, at the beginning, you're transmitting on frequency 4, then to frequency 2, and then to frequency 5, and such and on. And you take that and you calculate the radar ambiguity function by using that mathematical formula I said before, and you get the bottom part, which is essentially your estimate of how good this code is. Remember, we're looking for something that only has a dot in the middle and not much else everywhere. That's pretty good. This, by the way, is for the sequence that you see on the right-hand side, K1ABC from W9XYZ at grid square EN37. So one message on its own looks pretty good. It looks pretty random in that 15-second interval. But there are some side lobes visible. If I plotted that in a log scale rather than a linear scale, you would see that, in fact, there are some responses not in the center that are mixing a little bit of information. And did we happen to pick a message that coded into a quasi-random sequence by total luck? We wanted to check that. The way to do that is something called Levenshtein Distance. This is Vladimir or Volodya Levenshtein, who received the IEEE Hamming Medal in 2006. This is a general metric for measuring the difference between two sequences. There's two examples on the left and the right-hand side. You can use this for strings, like I want to take the word kittens and transform it to sitting. Takes me 3 steps. So the Levenshtein distance between kittens and sitting is 3. Or on the right-hand side, I've got some numerical sequences, and the distance between A and B, for example, is 1, because I only changed one number to get from A to B. So this we're going to use as a tool. Let's see how random a range of FT8 messages is, rather than just one. The more random, the better we can make this by piling together multiple sequences. So pretty much the last thing I will tell you is this is how it comes out. That antenna that you can sort of see in the lower left-hand corner is my little, extremely modest fan dipole in my backyard, not even that high. I have an FT8 receiver running on a red Pitaya pretty much continuously. And on the January 2nd of this year, it collected 38,567 spots from 8,000 plus unique calls. We took that database. And on the right, what you see is we compared every message to every other message and assessed its randomness using the Levenshtein criterion, which is almost 1 billion different message pairs. There's an example there on the left. And we did the histogram. How far were these apart? And if you look at the histogram, it turns out that they were on average apart by about 41 or 42 changes in the message. Remember, the message length is 58 symbols. If they were perfectly random from message to message, they would be at 58. So that sequence sense is reasonably random. And in fact, that's even a little bit better because all of the messages, we started out with W1PJE because that's where I was receiving them. So that's inherently a non-random element. And still, that message sequence was pretty random. This is good. That means that we could take 7 or 8 of these codes over say, a 2-minute sequence and stack them as long as those receivers were in about the right direction for better performance. So just as a summary, this is kind of where we've gotten to right at the moment, is that the coding that is built into FT8 means that even though you're sending a coherent message, my call sign, your call sign, location, the coding randomizes it really well. Makes it a pretty good radar signal. And now I've shown you also that I can take multiple of these sequences, string them together, and improve the randomness. However, it's a work in progress because what kind of Doppler and range resolution did we get out of this? Well, the Doppler resolution is about 1 over the sequence length, which is actually a little bit less than 1/10 of a hertz, which is pretty good. Ionospherically, that's about 10 to 15 meters a second velocities. That's all right. The range resolution isn't so hot. FT8 occupies a bandwidth of 50 hertz. If you flip that over, that's, oh, I can tell you where we are to 1/2 an Earth radius. That's not so hot. But there are more exotic super resolution processing techniques where essentially you oversample the signal and then you go ahead and try to synthesize more range out of it. They may help. That's a future study. But I think this kind of has, if you can imagine a bunch of personal space weather stations out there collecting FT8 signals in this manner, I think there's some real possibilities here for doing basically what we call passive radar, which is just a radar where you don't control the transmitter, with all of these huge numbers of FT8 signals flying around out of there. So stay tuned, work in progress, but hopefully this will be a nice application for the space weather station. And I'll stop there.
Thank you so much, Phil. That was great. It's really nice to see this because it really shows something that we can possibly use to make good measurements with an actual amateur radio mode. So people can operate their ham radios like they do right now. We can provide a good way of collecting that observations back for the ham radio community, and we can also collect some good ionospheric data from this as well. So we are right up against another break, so it's just about lunchtime now, but we'll take a couple questions before we put it into open webinar mode.
Yeah, Phil, Gareth here. I got a question from Anton. It's about that figure you have up on your slide right now on the top left. About the color code. I think he's wondering what.
Oh,
the
like
color
let me back up that one right there, huh?
That's correct. Yeah.
Oh, the color code is literally just to show you that wherever there's yellow, that means I'm using that frequency bin, and whether there's blue, it means I'm not. And if you look, I'm only using one frequency tone at a time. So if you look across, you'll notice that there's never vertically more than one yellow block. So that's what we call it a stencil. It's sort of like an old punch card in that we punch one column at a time, and then as a function of time, so if you ever turn on an FT8 signal and put it in your headphones and listen to it, you hear this warbling frequency, but there's never more than one tone at any particular time.
Thank you very much.
Phil, I had a question.
Yes.
For Phil. When you were doing the talk about the Levenshtein analysis, I think you made the statement that you thought that the call W1PJE appears in all the messages, but that's only true if the station is calling you. I mean, if you're saying using like a red pitaya to collect FT8, there's not going to be a whole lot of messages in 38,000 messages that have your call sign in the W1PJE.
I completely agree, Bill. And what we just did was, for this particular thing, we just started with I was always one of the stations, okay? You are right. In a general station that is receiving call A to call B, the only caveat I will put on this is that I think our analysis only extended to messages that had the receiver and the transmitter and the grid square. Because we figured, we want to using this for remote sensing, so you want to know where would this one of the stations is coming from. If you look at FT8 traffic, there's a bunch of things that say RR73 and other kinds of things. We didn't analyze those. So this is, again, it's just the beginning.
Yeah, okay.
One more question?